The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
It is my pleasure to introduce you to Professor Jim White, who is a professor at the University of Michigan in Ann Arbor, and who will be presenting a paper on historical development of design provisions for reinforced concrete beam-to-column connections. And it's my pleasure also because he is El Presidente of ACI to become El Presidente. So welcome, El Presidente.
Thank you, Sergio and Jose. Thank you also. I really appreciate being asked to make a presentation during this symposium. My colleague Gustavo Para-Montesinos is a co-author on the paper, but he does not need to take any blame for this presentation. Anything that goes wrong is mine. I wanted to spend some time talking about the historical development of the design recommendations for reinforced concrete beam-to-column joints. It's something that was really intimate to the early part of my career, and so I think I know it pretty well, and I possibly know it too well because I had a lot of trouble deciding exactly what should be put in here, and I may be running a bit late. So as I said, if I'm running late, please let me know. I'll be happy to yield the floor. I'll talk about some of the initial research, but not very much detail, and then we'll spend a little bit more time on the first committee report from Committee 352, and then we'll talk some of the additional research and evolution that went into the second committee report in the mid-'80s. And then as I'm going along, actually, I'll have some of the discussion of how these items were eventually adopted into the 318 building code. And I may or may not have time for some additional modifications that have occurred and some of the coordination that occurred with Japan and New Zealand. The problem with beam column joints, really there was not a lot of documented failures that were occurring in beam-to-column joints because we really didn't have good column designs, and many times the collapses were due to columns. This is actually from Venezuela, but there was this thought that if we started at least getting it right with the columns, we may have some problems in the joints, especially if you didn't put any confinement reinforcement in the joint. And so there was some research going on. And some of the earliest papers that I had been in contact with came from the Portland Cement Association, Hansen and Connor, and then Hansen on his own, a couple of papers that appeared in the mid-'60s, early 70s. Park and Pauly in New Zealand were taking a close look at this also, and they actually had a series of papers. I haven't highlighted all of them. This is one that appeared actually in the Fifth World Conference on Earthquake Engineering in Rome, and that was actually just after I had graduated. I was able to go to that particular conference. Up in Toronto, Uzmeri and Sechkin had a report that came out in the early 70s. But anyway, Professor Uzmeri was quite busy with this. And clearly the Japanese were also looking into this particular problem. So there was a lot of research being done around the world. Most of it was being done on most of it was exterior connections. A few of them were interior connections, and a few of them had some transverse beams, but almost none of them had any slabs. And so a lot of the criticism of the early research would be, well, what would happen when you add a slab, and et cetera. But anyway, this eventually led to ACI forming ACI Committee 352. It was formed in 1966, and the initial chair was Meta Sozin. The second chair was Jim Jirsa, and he was actually the chair as the first committee report came out in the mid-'70s. It came out actually in 1976, and it was a set of design recommendations. And this is actually a shot, and I thought it was very interesting to look at some of the people who were on this committee. Norm Hansen from PCA was there. Meta Sozin is down here. Here's Mike Uzumeri, Loring Wiley. I saw him come in. Raymond Rees, Clarkson Pinkham eventually became a chair of the committee. George Lay, who was chair of 318 and eventually became the executive vice president for the Institute. Bob Park, Raymond Hayes, very good names, Vit Botero. And I'm probably not going through all of them, but it was really a very strong committee that was put together here to come up with these design recommendations. And I thought some of the key topics in that first paper were really the confinement required to transmit the axial force through the joint. This is really a key thing that was in the original report and continues all the way till today. One of the things interesting in that first report is that it was kind of modeled on the ACI building code, and the joint shear strength actually was made up of a concrete contribution and a steel contribution at that time. There were equations for hooked anchorage reinforcement, and I'll get to that a little bit later. There wasn't anything on straight bars passing through a connection. And at the very end, there seemed to be a little bit talking about the required column flexural strength, making the column just a bit stronger than the beams that we're framing into it. One of the key things that appeared in that first joint report was that they divided their recommendations into Type 1 and Type 2 joints. Type 2 is really where all the research was, where we were looking to get both strength and ductility out of the connection, but they thought there was the need that we should also talk about just Type 1 joints, which would be kind of a non-seismic design where you only concentrated on strength. One of the important things in that first committee report also was the concept that the stress in the steel reinforcement, the primary flexural reinforcement, is going to have to be multiplied by a factor multiplied by F sub y. The very first reference in that first report was my thesis. Meta Sozin, of course, was on the committee. But we, by strain gauging some rebars, we were able to show that very quickly after a bar yielded, it quickly proceeded into the strain hardening range. And so this was something that was coming out of at least my work and some other work going along. It was limited to normal weight aggregate concrete and beam widths less than or equal to the column width. The confinement requirements are really the same that we have in the codes today. If you happen to use spiral reinforcement, and there's not many people who use spirals through connections, this is the equation that's currently in the ACI building code. And this is the minimum percentage. This actually kicks in when you have some larger columns, and this ratio of the gross area of the column to the confined core approaches 1. This equation takes over for larger columns. I've just highlighted this coefficient of 0.12 here because it also appeared when we looked at ties for confinement of the reinforcement. I got a little error down here, I'm sorry. The clear spacing greater than or equal to 1, less than or equal to 3. This is what's really in the code today. So no difference there, but appeared in the 76 version. For lateral confinement with ties, we have an equation that is actually the same as still appears in the ACI code today. It appears in the Committee 352 report. It appeared in the UBC code used on the West Coast. And again, whether this was a mistake or not, this coefficient of 0.12 also appears here, exactly the same coefficient that was back here for a spiral. But it's actually quite a different coefficient here when it applies to tie reinforcement. And I'll talk about that a bit later. But through the joint, I hit the wrong thing. The stirrups were to be at a spacing not exceeding 4 inches. And this is actually a figure from the current commentary, and I apologize for the quality, but I just thought I'd try and just use some of the actual figures that are used in codes and et cetera. And the idea here is that if you're using a tie, I'll get straight on this sooner or later. And let's say that you were trying to confine for expansion in this direction, so these 3 legs were what you were using for the confinement reinforcement, then these 3 legs would be that area that we had in the previous equation, and this would be the width of the confined core. And then similarly in the other direction, you have 4 legs, and the width of the confined core goes from the outside of the tie to the outside of the tie. Those are some things that have been pretty constant over the years, although maybe the notation has changed. One of the things of interest was the shear strength, and there kind of was a bouncing back and forth between stresses and forces, but the shear strength that had to be designed for was some sort of a calculated maximum shear occurring in the joint, and then dividing that by phi and A sub CV, and that's the effective area of the joint, with phi being equal to 0.85, and that has stayed. A sub CV was either the width of the core times the effective flexural depth, or it could, in certain cases, B could be increased to the total width of the column if you had confining members, lateral confining members with widths exceeding 3/4 the width of the joint and 3/4 the depth of the joint. Again, that is a type of notation that's been continued up until today. This is just a sketch, again, from the original report where it indicated here was B prime was just the size of the core, or you could maybe take the full B if you had adequate confining beams. And the idea of getting confinement either from the reinforcement or members framing transversely into the connection has stayed. This figure also showed the shear reinforcement, and there was a little statement that all of the shear reinforcement you put in the joint had to be between the upper and lower layers of beam reinforcement framing into the connection to be effective. This calculation of joint shear is pretty much the same that we talk about today. If what I'm indicating here, this is the overall joint, and it's being subjected to a reverse type of moment through the connection, so that you have tension on this side in this reinforcement, and you have tension on this side over here in this reinforcement. If you take this beam and put it into equilibrium, this T2 force is equal to that C2 force. So you have a total force from the beams going in this direction, and therefore you get a shear in the joint that you need to resist. There is a shear also in the column that is normally calculated from a simple equilibrium, assuming there's points of inflection midway up the length of the column here and here, and knowing the moment capacities of the beams. And this is really what we're actually calling the probable moment capacity today, because we're taking F sub y, multiplying it by an alpha value, and dividing it by L sub c to come up with a value for that shear in the column, and then you can just go back, and with that, then you have this shear in the joint that you're designing for. Now, as I said, in the 76 report, there actually was a V sub c term, and it's given here kind of a complicated-looking equation, but it's in, again, a stress unit. And again, it involved the axial load, but there's a statement down here that for type 2 joints, they normally recommended taking the axial load equal to 0. Again, the gamma value could be increased if you had lateral confinement from the members. Again, width of at least 3/4 the width of the joint and 3/4 the depth of the joint. Otherwise, gamma would be dropping down to 1. A beta factor was also in there equal to 1 for type 2 joints, for type 2 joints and 1.4 for type 1 joints. So that would give you a V sub c term, and again, we had to have a V sub u that we needed to resist, so then you would go ahead and add enough shear reinforcement to give you that V sub s term, basically the difference between V sub u and V sub c. And this is really just a normal, assuming a 45-degree crack in the joint, so this is almost like they had for beam design in the main body of the code. And what it seemed to be saying is that if you put in more and more shear reinforcement, you could resist more and more shear in the joint. And so you end up, actually the design example in that first committee report, I know you may not be able to see this clearly, but I'm not really sure anybody could have ever built that particular connection. There seemed to be bars running in all kinds of directions there. But anyway, this was the design of an exterior joint. For the anchorage, the only consideration was of hooked bars. There was no discussion of straight bars passing through an interior joint. And interesting, at this stage, there actually was the required calculation of a straight length before a standard hook. There was a certain amount of strength given to a standard hook, and then to get the full development, you needed a straight length before that hook. The anchorage was assumed to start at the front of the confined core instead of the actual face of the column, and you were always advised to move the tail to the far side of the joint. And so again, these are some figures. Actually, in a type 1 joint, you're able to use a straight bar, but I don't think that's going to happen very often. But here, down here for the type 2 joint, again, you move the hook as far back as you can. You're going to get a certain capacity out of the hook, and then there needs to be a minimum straight length before that hook commences. And again, some of the equations here, some of the work that Jim Jirsa was doing at that time on hooked bar anchorages. This does appear as a reference in the committee report, and this is the equation then for how much a standard hook could carry. Again, there's a factor here, 1.4 if the diameter of the bar is less than or equal to a number 11. You have side cover greater than or equal to 2.5 inches and tail cover greater than or equal to 2 inches. Those are the same words that are in the ACI building code today. You actually could go up to a gamma value of 1.8 if you also had ties at a spacing less than or equal to 3 inches, and there is a similar sort of thing in the ACI building code today. So there was some credit given for confinement on this value for the hook. And then clearly if the hook could carry a certain amount of stress, and the total stress in the bar was alpha times F sub y, then there was a calculation for a required straight length before that hook. And so this is the way things were done in that 70s. Again, I think that was a very exciting report, and there was a lot of research then that was going on while that report was coming out. Again, some people may not be here that should be here. I think some of the work that Don Meinheit had done with Jim Jirsa kind of proved that the idea of adding more and more shear reinforcement and getting more and more strength didn't work. There was some upper limit. And it really turns out that if you just confined the joint very well, you could carry a certain amount of shear, and putting in more lateral reinforcement really didn't do you any good. There was some work that I did when I first got at the University of Michigan with a PhD student, Dwayne Lee, and Bob Hansen was there at that time, where I think we pointed out the importance of the moment strength ratio, the relation between the moment capacity of the columns and that of the beams. Of course, Jim Jirsa had some other students working with him. Zhang, and I may not have the correct pronunciation, and Jirsa's paper was used quite a bit for the adding on to the 76 report, and some additional students working with Jim. And then I had a couple of students at the University of Michigan who worked with me where we did some interior and exterior column connections with and without slabs to see if there was any difference. And that's Mo Asani, who has been at the University of Arizona for a while, and Ahmad Durrani, who's been at Rice University for quite a while. In Toronto, Shamim Sheikh was working with Mike Uzumeri, and I think they did a very important thing talking about the confinement of well-detailed tied columns and came up with some confinement equations that I think are actually very good and actually were quite useful. And, of course, we had Park, Pauly, and now Priestley providing us some additional information from New Zealand. So there was lots of research being done, quite a hot topic, I would say, leading up to the next committee report. And so the next committee report actually came out in 1985. Clarkson Pinkham was the chair. I was the chair of the subcommittee, and I was actually in charge of writing that next report. We went through 13 drafts before we finally got that out of committee. And it seemed like part of the problem was we just had too many people who had too many good ideas. Again, Mike Uzumeri was still on here. Loring Wiley was still on here. And Loring, actually, it was an interesting dynamic. It was had Robert Park on there. And the New Zealanders kept saying we need more and more and more. And Loring said we need less and less and less. Otherwise, nobody will ever build any of these. And so it was really quite an interesting dynamic. Of course, Jim was still on the committee. Kerry Kopczynski joined the committee as a practitioner, and he was very useful. And Vit Patero was still there. But actually, Jack Maley started coming to the meetings. And giving us all kinds of trouble, asking tough questions and all of this sort of stuff. So, and I didn't realize it, but his name actually wasn't on this, and it's too bad because he did contribute quite a bit to it. Again, we started having these nice figures that we were going to cover interior and exterior and corner connections. And the truth is we didn't have research to really know all of the answers, but we did the best we could. The key factors in the 85 report were, the shear strength, confinement, moment strength ratio comes in, and then reinforcement anchorage. And now we included some provisions for straight bars on an interior connection. Again, as I said, the work by Meinheit and Jirsa was the one that indicated that adding more transverse reinforcement didn't do us a lot of good. A well-confined joint could carry a certain amount of shear stress, and quite a bit more shear stress than had been assumed in the 76 report. And therefore, V sub n would just be calculated directly, and there were no longer calculations of components V sub C and V sub S. And so we end up with a fairly simple equation that the reduced nominal strength needs to be greater than V sub U, and that's determined as we showed previously. And again, the phi factor was 0.85. And we have an equation that's actually stuck in both the committee report and now gone into the 318 code, where the nominal strength is some gamma factor multiplied by the square root of F prime C times some effective area of the joint. Now, for the joint, we dropped the D value and took the total, if you wish, depth of the joint. There is some discussion of the width of the joint that I'll get to in a minute. But we came up with this table. Again, most of the research was really being done for type 2 joints. And I think these numbers are what we keyed off of, 20 at an interior joint, 15 at an exterior joint. We didn't have that much on corners, but we knew they weren't confined as well, so we went a little bit lower there. And then for type 1 joints, where we weren't really testing them at all, we just bumped all the numbers up a little bit to come up with the numbers that are shown here. But one of the key things then was the effective width of the joint. Again, we were looking at beams less than or equal to the width of the column. If the beam was narrower, then the width of the joint would be either the average of the beam width plus the column width, or there would be some projection off the side. And I'll show you something that actually kind of indicates what was being done here. If you had a beam that's narrower than the column, then you were able to project along the line, and when you got to the mid-depth of the joint, that would be the width of the joint. This may or may not be the governing criteria. I've drawn this here with this S value here indicating a slope indicator. We were assuming at that time a 45-degree angle, but since this is an eccentric joint, there actually was some discussion of making that shallower if you had an eccentric joint. And then actually when this went into the 318 code, Jack Maley came up with yet a different way of doing this. But again, if you happen to have a narrow beam centered on a wider column, then it wasn't as punishing as having a narrow beam at the edge to account to the effects of having some eccentricity in the transfer of forces. But anyway, then this is what we did for the shear capacity. Confinement requirements, there were some changes made to reflect the good behavior of a well-detailed tied column. Again, previously, I think they had been punished a bit too much. And also there was a statement that the confinement reinforcement could be reduced by as much as 50% for an interior joint if it was confined by lateral beams. And again, the definition was the beam width was 3/4 of the column width, and the depth of these confining beams was at least 3/4 of the depth of the deeper beam framing in there. One of the things that I ended up spending quite a bit of time on was trying to talk about the difference between confinement from spiral reinforcement and tie reinforcement. And here I'm just kind of showing a perimeter tie and obviously a spiral giving you a perimeter here. And you might get a little bit better confining coefficient if it's a spiral than a tie. And so therefore maybe the coefficients should be different. But if you do the work here, for a spiral reinforcement, the rho sub s is what needs to be greater than this 0.12 times f prime c over f sub y for the transverse reinforcement. And if you do the definition for the volume, or the rho value, it's on a volume basis, volume of confining steel to volume of the core, you actually end up with a coefficient of 4 times the area of the spiral bar divided by the diameter of the core and the spacing of the spiral. If you do it for the ties, the way we had that, the coefficient is actually 2 areas of the bar. Just going back here, this is it. You've just got these 2 bar areas. And we were indicating that that also had to be greater than 0.12. So the ties were given about 50% with respect to the quality of confinement from ties that you had from spirals. Again, based on some of the work of Sheikh and Uzumeri, I think we were able to make an argument that that should be changed. We changed it to 0.09 in the 352 report. UBC had it as 0.12 for a bit longer, but eventually they changed over to the number that we were using, and that's the number that now appears in the 318 code. The moment strength ratio, this was kind of an interesting story for me. Normally, when you're designing a frame, you want to have a strong column, weak beam type of behavior. And again, I think that this was not thoroughly thought out in the 76 report. There was just a little bit of a calculation near the end. And actually, one of the first things that I tested at the University of Michigan, and this was with a doctoral student, Dwayne Lee, I'd sent this design down to Metasozen before we tested it, and his question to me, why test that? It's going to fail immediately in the joint. So I was feeling kind of bad, and we went ahead and tested it, and this is what happened. The joint was fine, and all the failure was out here in the beam. And what happened is that the strength of this part of the column was already as strong as this part of the beam, so the ratio between the total flexural capacity of the column to that of the beam was more than 2. And when you had a high, if you wish, moment strength ratio, all of the damage tended to stay here in the beam rather than penetrating into the joint, even though the joint appeared to be under-designed. So therefore, that ratio between the moment capacity of the column and the beam became fairly important. And we had all kinds of arguments about this. It ended up that what went into the 318 code and what came out in the Committee 352 report was that ratio between the column moment capacity and the beam moment capacity had to be at least 1.2. Some of us on the committee were fighting very bitterly to get 1.4, but we were pushed back. And again, Loring, I'll give you credit for that. We were pushed back to 1.2. He said, if you want concrete buildings to be competitive with steel, you can't go to 1.4. Bob Park, on the meantime, was telling us it should be 1.8 or something like that. So we were getting kind of hit. The New Zealanders trying to get us to go higher, Loring Wiley getting us to go lower. Anyway, this number went into the code, and surprisingly, instead of showing 1.2, like that's too many significant figures, they changed it to 6/5 when it appears in the 318 code. A subtle change, but that's the way it still appears today. Reinforcement anchorage, The new equations are actually now directly for a formula for the development length of a hook. And there also were some details developed for straight bars passing through an interior connection. At this time, we still were talking about the development starting at the face of the core for a Type 2 joint, for a Type 1 joint, assuming it starts at the face of the column. And again, for both of them, we would be using alpha f sub y with alpha 1.25 for Type 2 and just 1.0 for a Type 1 type of design. These are the equations that are in the, these top two are the ones that appeared in the report in the mid-'80s. And actually, these are very similar to what's in the code today. This is actually the same equation that appears in the ACI code today. This is the one that we had for Type 2 joints. Again, increasing to alpha f sub y in the numerator, but going to a coefficient of 75 in the denominator. And you might wonder, why does a Type 1 joint have a different coefficient in the denominator? Well, it doesn't have as much confinement reinforcement. So because of the better confinement effect in the Type 2 joint, we actually had a higher coefficient here. Again, 318 doesn't like to accept things from other committees, so when it went into the 318 code, it was modified a little bit. The alpha disappears now, and the coefficient 75 changes to 65. To be perfectly parallel, it should have changed to 60, but it didn't. So anyway, a little bit different in the 318 code today. And the other thing we looked at was a situation where you could have a bar acting in tension on one side of the joint and compression on the other side of the joint. It'd be very unusual to have the bar yielding in compression on this side of the joint and yielding in tension on this side of the joint. So this is by far a very extreme case drawn here. But clearly, the bond stress is going to be related to the relationship between the diameter of the bar and the length of the joint. So again, we had another good time trying to come up with what this coefficient should be. Many of us on the committee wanted that coefficient to be 24. Eventually, it got moved down to 20. And you know who was helping us out, Loring. But anyway, we got that down to 20. Roberto Leone wrote a beautiful paper about 4 or 5 years after we got this out and clearly showed that if you had it up at 24, you had much stiffer behavior and much fuller hysteresis loops than if you stayed at 20. But anyway, this eventually did get into the ACI code, so this is in the ACI code today. The other thing we looked at is that, well, if beam bars could slip through a connection, column bars could also slip through a connection. And so we also recommended that this ratio be used for the depth of the beam and the diameter of the column bars. Same coefficient, 20. That never got into the 318 code. But very interestingly, this was coming out in the mid-'80s, just about the same time of the major earthquake that affected Mexico City. And I remember Sergio coming to me and saying, can we get this into the emergency provisions for the Mexico City Code? And this is in the Mexico City Code, even though it never got into the 318 Code. A few things that have happened since the 85 report, and I'll give some different people credit, but John Wallace, I remember him bringing to us some anchorage provisions for headed bars, and maybe that would be a way to cut down on all of the confinements or all of the steel in the joint. I've done a lot of research on beams wider than columns, so eventually there were some changes to the 352 report to allow beams to be wider than the columns. And I also have done quite a bit of work on eccentric connections, and one of my former students, Jim Lefebvre, has done some of that work also at the University of Illinois. Other things that happened, and Jim Jirsa was very much responsible for this, there was a series of 4 coordination meetings between the New Zealanders and the Japanese and the U.S. practitioners. And there were a series of meetings that occurred over these years. This is actually as the second report was being finished, but through the 80s. And eventually this came out as an ACI-ASCE 123 on design of beam column joints for seismic resistance. Jim Jirsa was the editor. This appeared in 91, and there were many very interesting papers that appeared. But I think these coordination meetings actually brought the design provisions in the 3 countries closer together. They all are a little bit different. The New Zealanders are obviously a little more conservative than the ones we have in the U.S. And I think the Japanese, Shun, you can tell me, I think they kind of fall in the middle. But there are a lot of similarities between these. And so somehow I did get all the way through this. Thank you, Jim, for all of your work, for beam column connections, and thanks to you in the audience for your attention.